Okay, so in NMR, we were talking about that any material to induce a magnetic field or to get interacted with a magnetic field, it itself has a spinning charge, because the static charge will give you the electric field and the magnetic field would only be coming from the movable charges. So we got to know that nucleus is having both spin as well as charge, and therefore it creates its own magnetic field. So as soon as we are giving a B naught magnetic field, that induced magnetic field starts moving around this magnetic field in certain direction. That is called, just like a top. If you have seen a top, if you just place it and rotate it in a field, it would be having certain kind of motion. That motion is called as a, this is called a precession. That motion of your particular induced magnetic field in presence of your external magnetic field. And depending upon that, we talked about how different spins can be oriented. And we took a case where proton, that hydrogen, that H is having I value of half. And if there is no magnetic field, both the states, the two states that are possible, that Mi plus 1 by 2, Mi minus 1 by 2, they would be at similar level, that is called as degenerate level. As soon as the magnetic field is involved, one would orient in the same direction, that if my magnetic field in this direction, my spinning would also happen in this direction. But if the other case, it is going above and the other one is going down, that is a case where it is orienting in a different direction. The one which aligns with that, that is alpha state. The other one which opposes it, that is beta state. So in this way, we defined it. If we took another case that I equals to half value, there would be two combinations, alpha alpha, beta beta, that is -1, that is +1, and alpha beta or beta alpha. So these kind of combinations are possible when we are applying a magnetic field. And depending on these transitions only, we see a different NMR spectra for different nucleus. Why this transition happens when we are giving a radio frequency and that exactly matches with the gap of these two states, then the transition happens, and we saw these spectra in the NMR spectroscopy of the instrument. So after that, we saw this we have covered. Then we talked about different magnetic radiations, electromagnetic radiations, starting from the cosmic rays and going to the radio waves. This is based on the energy factor. Cosmic have the maximum energy, radio waves have the minimum energy. Radio waves are used in the NMR. And then we talked about different abundance and how different frequencies are being taken for different nucleus. You have to be very careful which nuclei are NMR active and which are not. If they are having same number of protons and neutrons, and even in even, that they won't be able to give you NMR active species. After that, we talked about the electron spin resonance. So similarly, the way it happens for the nuclear spin state, it happens for the electronic spin states. In presence of the magnetic field, there would be a transition, and they use microwave radiation, because any energy state, any species to go from a ground state to the excited state, it requires some quantized amount of energy that comes from the electromagnetic radiations. And depending on that, we get an electron spin resonance. And lastly, we talked about the gamma radiations that are being used in the Mossbauer spectroscopy. That's the second part of our course. And here we saw if the radio waves are being given, the transition of the states would happen from the similar nuclear spin states. That within the I equals to half, there would be two values, plus half and minus half, depending on the orientation. Then the transition would happen among them only. But if you are providing gamma radiations, there would be a transition in between two different spin states or more than that. So that comprises of the Mossbauer spectroscopy, which we will be taking in details in the next week. So before starting assignment, is there any doubt, any query regarding what we have talked about? Because that would become easy for me and for you also to solve the assignment problems. Is there any doubt?
No doubt, ma'am.
So I expect that now you can solve these questions. So today we have taken the 5 questions. I hope that would be covering almost all the concepts. So the first question is the signature bands for hybrid topology of G complex. We saw the 3 different parallel, anti-parallel, and the hybrid one. So can you please tell me which one is having the hybrid topology, the signature bands?
B option, ma'am, plus 295, 260, plus 240 mm.
B option or which option you are saying? Can you please repeat? Is this B or D?
B option, ma'am.
Like last one?
Yes, ma'am.
Okay. So as we saw that, okay, the hybrid one is having 295 and 260 as positive, 240 as negative. So here we have 295 and 260 as positive and 259. So this is our right option. Corresponding to that, you can identify the parallel and anti-parallel also. Now the second question is, which of the following statements is right? Okay, so this part we have not actually taken. So I have to explain first, and only you can answer that. Okay, we'll take this question later. The third question is, which of the following statements is or are right about the NMR spectroscopy? So whenever these kind of questions occur, there could be possibility that one answer is correct or multiple answers are correct. So you have to see all the answers. So firstly, in NMR, transition happens within the same nuclear spin states with opposite signs. Is this correct?
In NMR transition happen within the same nuclear spin state with the opposite sign. No, ma'am.
But it is happening, no? When we are having I equals to half, it goes to plus 1 by 2, sorry, minus 1 by 2, plus 1 by 2. So these are the similar same spin state, but opposite signs, right?
Okay, ma'am. Okay, ma'am.
If it goes from 1 by 2 to I 3 by 2, then that is the Mossbar spectroscopy. But in NMR, that has to be in the same spin states. Okay? So the first option.
Okay.
Radio
First option,
frequency is used
yes, ma'am. NMR radio.
for different nuclei. Radio frequency so required is same. If I'm taking proton, now I'm taking carbon, both will be using same radio frequency or it would be different?
Radio frequency is same, ma'am.
No,
For
actually,
different nuclei.
for different nuclei, actually this radio frequency role comes when we talk about the magnetic moment. So there are so many factors that we have to explain. So normally, if I'm using 500 megahertz for proton, it normally uses 126 megahertz for 13C. So this value would be different if I'm using a phosphorus nuclei. It would be different for a fluorine nuclei. So all the nuclei, since they are having different magnetic moments, that's why because of the different magnetic moment, they require different radio frequencies. That okay. So for different nuclei,
Okay,
different magnetic moment, different frequencies. So they can't be same. So C option is not right. The active NMR nuclei should possess I value greater or equal to 0. Is this statement correct? I told you that NMR nuclei, the nucleus to be NMR active, what value it should be having? Either it should be I equals to 0, I greater than 0. So in this particular case, it should not be having I equals to 0. Other than that, I greater than 0, any value is NMR active. So here it says that I value is greater or equal to 0. So this is half correct, half not, because it can't be 0. If it is 0, that can't be NMR active, and therefore you will not get any NMR signal. So this statement is also wrong. Is this fine now?
Okay, ma'am. Okay, ma'am.
No. So now attempt attempt the fourth question. Arrange the following EM radiations in the decreasing order of energy. So we have already talked about what is the trend of the electromagnetic radiations, which is having the maximum energy. You have to put it at first, then greater sign, then the second, then so on and so forth. So choose the right option.
C option, ma'am.
Yeah, right. Because the gamma, it goes from gamma to visible to micro and then radio. So that is correct. That means you have understood the. Okay. Now the last question, choose the right option for mass bar spectroscopy. Gamma radiations are used in mass bar.
Yes, ma'am.
Transition is happening between different nuclear spin states or same nuclear spin states.
Different nuclear spin state, ma'am.
Electronic nuclear interactions. Okay, these 2 points we will be taking in next lecture. Actually, there is something called electron and nuclear getting interacted with each other that is called as hyperfine interactions, and they are very weak. So both all these options are correct, but we will take up these options in details in next week with some different questions. So this has covered all the concepts that I have talked about in this particular week. So the one question that has left is the second one, that histidine molecule. So there is something called racemic mixture. It is something when the isomers or both the forms. So for example, if in amino acids we are talking about, we have D amino acids and L amino acids. I hope you remember how do we give the D and L. Say for example, this is a general R, NH2. This is your alpha amino acid, and this is your if your hydrogen is at the back, this dash sign shows that it is back of the plane. So we use a con rule. Con means start 1 with the carboxylate, goes to second to R, and 3 to nitrogen. If 1 to 2 to 3, it is clockwise, that is D form. If it is 1 to 2 to 3, 1, 2, 3, if it is anti-clock, that is L form. So here we are going from 1 is here, 2 is here, 3 is here. So this is what? Anti-clock or clockwise?
This is clockwise, ma'am. Anti-clockwise.
Yeah, anti-clockwise. So this is L form. Similarly, if I am having NH2 over here, that would become a clockwise, that will give you D amino form. So based on that, if we are having in a particular amino acid, after certain operation, we will get both of them as 50-50%. That is called a racemic mixture. So racemic mixture is the combination of any two isomers which will present as a 50-50%. So that is generally happening in an enantiomer's case. So how do we? So what happens generally? Normally we know that our amino acids are mostly in L form. So with the passage of time in presence of the water, they convert to D amino acids. So they would be having something called half-life. Half-life is the time they will take to convert from L to D amino acids. So which ones is having, and this half-life is actually the racemization. So racemization means both are 50-50%. So which are having less half-life, that means they will easily convert to 50% L amino acid, 50% D amino acids. So that is called as the half-life of the racemization. So if I'll take an example of histidine, this is having more NH2 group, and valine, which is that isopropyl group. You have to go back and see that amino acids. So this is approximately having a, you don't have to remember the value, just in case. Just a second. Yes. So histidine having a half-life value of 5500, 5,500, and this is having 1,80,000. So it has been asked that why half-life is so less in case of histidine. That means it goes to racemization very easily, and valine does not. Why is it so? In case of the histidine, we have NH2 groups, that imidazole group is there. So in case of histidine, so in general case we talk about. So here we have R, this is H, this is COH, and this is NH2 group. So when it is going to, normally it exists in this particular form, Cr, COO negative, and NH3 positive. That is called zwitterionic form. So normally your any amino acids, they exist in this particular form. That is called the zwitterionic form in presence of water, because that is a source of H positive and OH negative. So it will give you a CO negative, and base will take your negative from this one. This will make a carboxylate, and the H positive will be attacked by the NH2 lone pair. So this is zwitterionic form. Now again, what can happen? They can form in presence of the acid H positive. It can form HO, the carboxylate group, and this, there will be hydrogen R and NH3 positive. So this H has been taken up because we have H2 over there. Now there could be possibility that this H goes away and it comes here. And what it will form? It forms C. Both oxygen are now hydroxyl groups, and this forms C+C, R, and NH3. Earlier, our carbon was not planar, it was non-planar. That's why it was chiral. Now, if you'll see, double bond is nothing but a symbol of planarity, because that stays in a planar state. So when planarity comes, that loses its chirality. Right? So again, because of it has to come back to its chiral form, so again it rearranges, and therefore it forms carboxylic group C negative. This goes over here. You can see this plot, because firstly we took the H positive, now it is again losing the H positive, and this double bond is going to the carbon, making it a carbon ion, and therefore NH3 positive. Now again this carbon ion, we know that carbocations, carbon radicals, cations or anions, they are planar in nature. So as soon as we form this carbon ion intermediate, now we know that when H has to attack, it can attack from any side, right? So when it attacks from any side, that half of the time it will go to diamino form and half will form L-amino, because you know that its orientation only is the factor which gives you two different isomers. So that becomes two sides for that H positive to attack on the carbon ion, and therefore it gives you a racemic mixture. That means both forms as there are equal possibility of having both the sides attack, either from this side or that side. That's why the D-amino and L-amino exist in 50-50%. So what happens when we get something which can stabilize this carbon ion, that will be having, which can stabilize, in case of the histidine, what happens here? In case of histidine, the actual molecule, if I am having this alpha, that carbon which is having H, which is having NH2 group and COOH group, this is having CH2 and NH. This is your imidazole ring. So as soon as this carbon, this alpha carbon is having negative ion, this gets stabilized by the inductive effect of your nitrogens. They are electronegative in nature. So because of that, that was stabilized by the imidazole group. And once it gets stabilized, that becomes high rate of racemization, and therefore its half-life in particular form that reduces. That's why in case of, whereas if you see the valine case, it would be something like this way. I'm just taking, that is aliphatic for sure. So suppose this one is your valine, and there is now negative. Now this negative, it is just the carbon and hydrogen, no stabilization of your carbon ion. That's why its half-life is very high. So it prefers to stay in one particular form. It does not go to racemic mixture. Whereas if with this negative anion is getting stabilized, it will go to racemic mixture, and that would reduce the half-life. Say if I have a certain material which, or we bought something, we bought a packet or any food or something that is having an expiry. So if I am not keeping it in fridge, it will get expired very soon. So I can't use it. So that expiry date, it's actually the half-life of your particular system. So here, when I am putting into the fridge, that is getting, if I am putting it in the fridge, it is getting more half-life. Similarly, it is happening when the valine is there. So it does not stay for carbonyl position for a longer time, and therefore half-life remains as such. Whereas if this state gets stabilized by that electronic charge distribution of that imidazole group, so once this is stable, it is having some time to get the attack from both the sides, from the left side also, the right side also. And because of that, we ended up having the equal number of D amino acids and L amino acids. So that's where the racemization happens. And the question says, now which one of the following statements is or are right? So histidine has more half-life for racemization compared to valine, because imidazole group stabilizes the carbon ion, or it is having less half-life because imidazole group stabilizes the carbon ion, or it is having more half-life because imidazole group destabilizes the carbonyl, or none of the above. So we understood that histidine group is having that imidazole, which is stabilizing your carbonyl, and because of that, it is having less half-life. So which answer is right?
B option, ma'am.
Yeah. So this option is your right. So it does not capsulate racemization. It is having less half-life in one particular. So did you get the concepts of what we talked about today in the whole session regarding the spectroscopy, and any doubt is there?
Ma'am, second question, B is correct, but D option is correct, ma'am. You pick.
Oh, actually D is only correct. That annotation goes above. Just a second. This is only correct. It got shifted. Yeah.
Okay, okay, ma'am.
Besides this, any other doubt you have regarding the lecture?
No, ma'am.
So this was all about the week 7 thing. Maybe now from week 8 to week 12, we will be talking and taking up all the concepts from the MOSFET spectroscopy, and that's a very interesting spectroscopy. There will be a lot of mathematical things, so you will be enjoying it soon. I would request that before joining this next session, you please go and watch the videos from the professor. just go through those videos once, and then it would be very easy to comprehend what I'm trying to say. Because in 2 hours, it's very difficult to talk about each and every concept that has been taken for the week thing. Okay. So with that, if you do not have any question, you can leave the session. Otherwise, if there is any simple or any doubt you are having, I'll be happy to answer that. Okay, since we have covered the topics from week 7 lectures, so I'll be meeting you guys in next week from 7 to 9 p.m. at the same platform. So if there is any query or doubt from any other live session that we had so far, I would be happy to answer your questions. So meet you soon in the next session. Thank you so much for joining.